So our first presentation is on NFO response, concepts and approach. That will be by Jordan Stout as our NOAA SSC here in California. Jordan provides scientific and technical support to Coast Guard, EPA, and many more, including certainly me and OSPR and everyone else. And yes, Jenna's posting the chat ground rules and everything else in there. Jordan's been involved in supporting many significant incidents in California, throughout the nation, numerous hurricane responses. He serves as NOAA's representative on RRT-9 and MEX's PAC Joint Response Team, and chairs the NRT's Science and Technology Committee. We are fortunate to have him as our SSC in California, without a doubt, and fortunate to have him here today. Jordan, take it away.
Thank you, Greg, and good to see everybody again. Let me pick my screen, and you should be able to see my slides. Okay.
Yep, you look perfect. Everything nominal. Thanks.
Okay, great. So I actually changed the title of my slide like 6 minutes ago to be response concepts and considerations for non-floating oils. But I think it gets at what we're interested in talking about. It might be a good groundwork for some of the upcoming talks as well. So, let's see. So I'm going to cover sort of some basics of different types of non-floating oils, some properties and behavior, and some transport considerations. I borrowed some slides from one of our oceanographers, Chris Barker, for that. And then some information and data challenges and needs that this whole concept has gotten me thinking about for what I would ask for in a command post if I was working on a non-floating oil spill in, say, a river system or something like that. So just to kind of back up and kind of orient people on kind of how NOAA gets plugged into sort of some of these things during spills. As many of you know, when there's a spill, NOAA often is focusing in on sort of 5 primary questions of what got spilled, where it will go, who and what it will hit, how will it hurt, and what can be done about it. For the purpose of this talk, I'm going to focus primarily on the first 2 questions and just barely touch on the 3rd question a little bit. We may get into some of the other questions with upcoming speakers as well. So I'll jump right into the what got spilled question. So if we're thinking about non-floating oils, there's sort of 3 ways to think about it. One is, well, first of all, most oils are floating oils. And so the 2 primary mechanisms, or the primary mechanism for floating oil to become a sinking oil or non-floating oil, is to interact with sediments, like on a shoreline or a river system or something like that. It's also physically possible. I mean, a floating oil will also, the density will increase as certain lighter ends evaporate off. So it could become heavier, but there's very few examples of a floating oil becoming heavy enough just due to evaporation for it to actually sink in the water column. And then there are some oils that are spilled that are heavier than water initially, and so they basically go straight to the bottom fairly quickly without any necessarily interaction with sediments or other mechanisms. So sediment interactions and possible evaporation can be a way for floating oils to become non-floating oils, and there's also non-floating oils that are inherently heavier than water to begin with. I'll go over some key basic properties. Obviously, density is a key property when thinking about non-floating oils, and I'm sure most people in the audience know that we use, as a density measurement for petroleum oils, we use what's known as API gravity, where API gravity in excess of 10 would be expected to float in fresh water. The thing about that, though, is if you have an oil of API gravity of less than 10, you not only need to think about the density of the oil, but also the receiving water that the oil is spilling into. Another important property to consider is viscosity, because that could affect the droplet size and the physical dispersion of a spilled oil in the water column. And that viscosity is going to be changing with things like temperature and as the oil weathers. So oils will typically get more viscous as they weather. Also, things like stickiness and persistence are both going to be elements in considering whether or not a spilled oil is likely to pick up sediments and potentially move from a floating oil to a sinking oil or non-floating oil. So to kind of focus on a density, as most of you know, fresh water, which has this is a graph of density salinity profiles or density salinity relationships. As most of you know, Fresh water is less dense than salt water. Here on the x-axis, fresh water has a salinity of about 0 parts per thousand, and typical salt water will have a salinity of about 35 parts per thousand. This is a figure from a recent API technical report. And looking at the density measurements on the vertical axes, you can see that an oil of an API of 10 or greater would be expected to float in both fresh water and salt water, whereas an oil of less than, say, API 6 would be expected to sink in both fresh water and salt water. But if the oil has an API gravity between, say, 6 or 6.5 and 10, then it would probably sink in fresh water, but it may float in salt or brackish water. So you really kind of have to be not only cognizant of the density of the oil, but also potentially of the receiving waters that the oil spills into. So, okay, now when we're talking about floating oils, which is most oils that might be transported and potentially spilled, the main way that a floating oil is going to become a non-floating oil is by sediment interactions, whether it's through getting spilled into a muddy river or a turbid river like Mississippi River, for instance, or a floating oil comes into a sand shoreline and interacts through in the surf zone and picks up a lot of sand. It could potentially, sink near shore, near the shoreline, near the surf zone. I'll show you a couple of examples of that to kind of demonstrate some of the top concepts I'm talking about. First, the Morris J. Berman spill in Puerto Rico in 1994. This involved a heavy fuel oil with an API gravity of 9.5 into a marine environment. So it was a floating oil, but it came in contact with beach sands, and the beach sand interaction was enough to make some of that oil sink in the near shore shallow bays. But this is Puerto Rico too, right? So some of those near shore shallow bays can heat up in the afternoon sunshine, and so it was because viscosity is affected by temperature. Sometimes the oil would get warm enough so that the oil and sand grains would separate from each other, and the oil would essentially sort of drip upwards. So this is an an incident where both oil density and viscosity were very important considerations in how the spill unfolded and some of the operational decisions that might be involved. Another one was the Athos 1 spill, which is in the Delaware River. This involved a heavy crude oil with an API gravity of 13.6 into a freshwater environment. So given that the API gravity was above 10, you'd expect it to float on the water. But given the nature of the release scenario, the oil basically was jetted into the mud sediments beneath or around the vessel. And so quite quickly, and so you had a lot of this oil that was released ended up moving through the water column or actually rolling along the bottom. So it became a much more challenging oil spill response than had the oil just been released directly to the water surface. So that's a situation where oil density was, or where sediment interactions was the primary cause of a floating oil to become a non-floating oil. So what if you have like a blended oil, like a diluted bitumen? So this is an example of one in the Enbridge spill in Kalamazoo, Michigan, back in 2010. The blended oil API was about 20, so you'd expect it to float in both fresh and salt water. This was spilled into a riverine environment, so it's a freshwater environment. As you can see in the picture near the release site, the oil was floating initially. One of the challenges about dilbit spills is that you have not one oil involved, but you have two oils. One is the bitumen itself, which is the heavier component, and you have the diluent, which is going to often be a lighter type of oil, maybe a diesel or a naphtha or something like that. And there's been the Canadians in the environment has done studies on dilbits, and here's some evaporation curves that they generated a few years ago, document cited at the bottom. The two left panels are different diluted bitumen oils. It shows an evaporation curve, and you can see how there's quite a bit of mass that's removed from the oil just based on evaporation. And so what that probably is the evaporation of the lighter diluent, leaving behind the heavier bitumen compounds. And so the oil that was involved in the Enbridge spill in Michigan was very similar to these two diluent or dilbit compounds or blended oils, and where it was initially floating, it evaporated quite a bit, and so it became more dense, but it was still light enough to float on the oil until it actually started interacting with the sediments. And so once it had spilled and evaporated and then interacted with sediments, then it turned from a floating oil spill to a sinking oil spill, and then the questions of detection and response tactics and all that sort of thing sort of changed dramatically from the surface oil spill to a non-floating oil spill. I'm not going to get into the tactics they use because I think other speakers may touch on that and for different non-floating oil spill case studies, but I just want to kind of give you an idea of how some of these physical properties are going to affect when and where you might start thinking about non-floating oils. So for inherently heavier oils, ones that are heavier than their receiving waters, you would expect them to sink. So then one of the big questions is, how far away from the source might you expect it to move? And that's really going to be dependent on the turbulence and the local currents. If you have a spill where there's virtually no current, and you'd expect the non-floating oil to spill and stay relatively close to the source, but of course, if there's a lot of currents or turbulence going on, then you would expect there to be some potential transport of those oils, right? So here's a couple of situations we can talk about, or case studies to kind of demonstrate this. One is the Dbo152 spill, which is actually the first spill that I worked with Jim Elliott on back in 2005. This is an interesting spill with a slurry oil with an API gravity of about 3.7, so you'd expect it to sink. It was also a very low viscosity oil and was spilled in marine waters in northern Gulf of Mexico, I think it was about 35 miles off Port Arthur, Texas. And as a demonstration, the command post, we grabbed a composite load sample of the oil and an aquarium filled with site water and squirted the oil into the site water. And you can see it went straight to the bottom. And interestingly, because it was a low viscosity oil, it formed oil droplets of lots of different sizes, right? And so our concept, our mental model for how this oil was potentially going to move through across the bottom was to think about that oil puddle on the bottom and a low viscosity oil, and if it was and it's probably sitting at about 50 feet, I think it was. And so when a big winter storm would come through, the surface waves would cause so much turbulence on the bottom that it would stir up the oil on the bottom and break it into droplets. And the large droplets would move short distances, and the smaller droplets would move much further distances. And so you get kind of this smear of oil across the bottom as it interacts with the local bathymetry. So that was a situation with a heavy sinking oil with turbulence. Here's an example of a heavy sinking oil with no turbulence. This is the APX 3508, which involved another slurry oil with an API gravity of -7.4, which is hard for me to wrap my brain around, frankly. But it was a much higher viscosity oil. It was spilled into a river environment, and it was a low current system, right? So if you think about, if you try to visualize how that oil might spill from the impact zone, impact portion of the barge there in the picture, you can envision just how it actually played out. They did another sort of command post or tailgate type of experiment. They grabbed some a load sample and some site water and poured it into the site water, and you can see it kind of looks like a thick molasses almost going straight to the bottom. And because it was a low current environment, you would expect that a bulk of the oil that was spilled probably wouldn't be expected to move too far away from the source unless situations changed, right? So just to kind of give you a sense of how some of these floating oils might behave in the environment, if you have a sense of some of the oil characteristics and the local conditions. So just to kind of wrap up the property and behavior considerations before I get into some transport topics. It's important to know what your oil is, and you can find that out certainly by chemical analyses, so although that may take some time. But chemical analyses are going to be way more informative for these sorts of questions than your standard safety data sheets, which are oftentimes very generic. You need to consider both the density of the oil and the receiving waters, as well as the potential for sedimentation and evaporation to be a factor in a particular response. For inherently heavy oils, those that are at or near or below API of 10, you also want to think about the oil viscosity, and the local currents and turbulent regime in the area, as far as how far away from the source do you want to be looking for oil. For Canadian crudes and dilbits, oftentimes, if you know what the oil field name of a Canadian oil field, you're going to have a lot of information available pretty quickly about how the physical and chemical properties of those oils, and probably a lot more than you would in a generic safety data sheet, but maybe not quite as much as you would for a chemical assay. So if you can find out the oil field name that the oil originated from, that could be helpful. But don't forget about, because a dilbit is a blended oil, to think about the weathering characteristics of both the oils and involved in the diluents. Okay, so moving on to the where will it go question. Certainly when you're trying to estimate transport of a spilled oil, on-scene observations are going to be critical. You have to realize that a non-floating oil is a much different situation than a floating oil and can be harder to see or track. Overflights are oftentimes very challenging in a non-floating oil. And so all of those types of on-scene observations are oftentimes used to calibrate trajectory models and transport estimates, right? So you need to be prepared for higher uncertainty in transport estimates for non-floating oils. There is a lot of information out there about ways to think about potential non-floating oil transport. If you expect it to be moving in the water column, then it could transport similar to suspended sediments. It's a relatively straightforward kind of time of travel type of question. But if it's denser than the receiving water, you could start looking at studies on things like bed load transport for beaches and rivers and different types of water bodies. But one of the things that's really going to be important to understand in interpreting those sorts of studies is how does that relate to the density of the oil you're talking about, and also the particle size of the oil that might have been released or might be stirred up in the different turbulent or current systems. So, droplet size could be a really important factor in estimating transport. It's going to be based on the oil properties and the turbulence, of course. There's been a lot of, especially since Deepwater Horizon, there's been a lot of research on suspended small oil droplets for things like dispersant studies. But oftentimes non-floating oils are going to tend to have a much higher viscosity and could potentially form a variety of different size droplets, including potentially very large droplets. And so there's not a lot of people out there that are modeling those sorts of mechanics and transport mechanics. So that's going to be a potential element of uncertainty in a transport model output. One of the things that we do have benefit of is some recent studies, including one from a PhD student at University of New Hampshire's Coastal Response Research Center, one of Nancy Kinner's folks, who was doing a bed shear threshold study using a sinking oil in different types of substrates with fresh oil and weathered oil, different temperatures and different current velocities. And I'm not, a technical oil transport person. I would rely on someone like Chris Barker, who spoke earlier this week about, the physics behind all that thought process. But I think it was a good first step, and I think it was really eye-opening for someone like me who would be going into a command post on an oil spill and saying, okay, we need to figure out where the primary surface zones are, right? So some of the information that got me thinking about that I would want to have access to is not only oil properties, but also what are the local current velocities, and recognizing that those are going to change spatially and temporally. What is the local substrates near the spill area and the distribution of those substrates? So there's going to be some spatial variability in that too. And also what's the local bathymetry, which is also going to have some spatial variability. And if you want to try to identify resources at risk, that might depend on things like benthic habitat mapping, which also has some spatial variability. And so some of those things like local substrate distributions, local bathymetry, and benthic habitats, to have reasonably high resolution spatial data on those types of data might be kind of challenging during an active response. So that might be something to consider. And you may have to, use a much larger search area initially if you don't have good information and try to narrow it down from there. But it's something to consider for non-floating oil response. So I think this is my last slide. As many people say, including our next speaker, every spill is different. And so for floating oil spills, the response community has a lot of experience in dealing with those sorts of things. We can bring a lot of experience to those sorts of incidents. But for some of the challenges with non-floating oils is we just don't have as many spill experiences to draw from. They're much less common than floating oil spills. As I said before, they're harder to see, harder to track, because overflights aren't necessarily going to do the job. And so transport models are going to be harder to initialize. Some of the properties of some of the non-floating oils are either not well understood or they may be variables, such as we had some of the incidents I talked about in this talk. Talked about 2 different slurry oils, which had different densities and different viscosities, even though they were both called a slurry oil. Mobilization of non-floating oils is going to be dependent on current and local current and turbulence, and the threshold mobilization thresholds may not be well understood for a given situation. And then overall, that you should expect some higher uncertainty in transport estimates, just because there's a lot of sort of data gaps in how we would need to be thinking through some of those things. So I will leave it at that, and I see my time is up. So any questions?
That was excellent. Thank you, Jordan.